There are 6 of these Fireflies, these satellites now ready to ship out and launch here. So 1, 2, 3, 4, 2 on the other side at the back there. It's not integrated on this satellite, for example, so you'll see that.
This looks good.
Yes. 2 more S-band antennas here, the star tracker that we on at least every face to make sure that regardless of which side it is, we can always know satellite is imaging. There's at least some sun angle to the solar panels, so generating some power. If not 100, looking at somewhere, this is where it's looking at. Thruster 2, thruster 1, and here. This changes a little bit in terms of the angle with the GPS satellites as such.
There's one
here, and then there's on every phase you have a out in the next 10 days.
This video is crazy. Like some of the things I will show you in this video, most of the global stars will not show. Obviously, this video has an actual satellite in it, but we also have a model where we can see each and every part inside the satellite. Like that is insane, that part of this video. And by the way, you can change the commentary of this video to Hindi if you wish. For people who have followed my channel since a long time and know about Pixxel, you can skip to this timestamp on screen. Others, please come with me. Pixxel is a startup headquartered in Bengaluru. It was founded by Awais, who is in this video by the way, and Kshitij in 2019. I had covered them in a video in 2020 for the first time, then again in a video where I spoke about hyperspectral imagery with the new satellite Anand, and now a visit comes full circle. They are working on a constellation of satellites doing hyperspectral imagery. What is hyperspectral imagery? While I have a dedicated video explaining it better, but a higher level explanation will be you can see much beyond your eyes and what other regular imaging sats can. The kind of imagery they do, not only can you know if a farm is dying or doing healthy, you can find mines, you can find where things are getting polluted, what is the source of pollution, forestry, and so much more. Most imaging sats out there can't do what their satellites can. So far, they have already flown 3 satellites to space. Most of them were demo or test satellites, but now they are building much bigger satellites called the Fireflies. So this is for their Firefly constellation, 3 out of which will fly within days of this video. I'll tell you more about them throughout the video as we progress through it. So welcome to those who skipped the intro. The approach to this video is something I would call premature contextualization. Basically means instead of me playing a video of Awais explaining something and then you wonder what he said and then I come in and explain you what he said, I will reverse this and I will give you prematurely the context and the explanation to the upcoming clip that I feel will make it easier for you to understand the concept what he is going to speak about. Every time I interrupt the video, this jingle will play, and don't worry, I interrupt this video like 6-7 times and the video is almost 1 hour long. So I would recommend you watch at 2x so it saves you some time. So Awais, what are we looking at?
Yeah, so this is the satellite that we call the Firefly. There are 6 of these Fireflies that are currently being built. There will be about 12 to 18 of these that will be launched in total. So the Fireflies are our fully commercial flagship satellites. The satellites that we launched before this, whether that's Anand or Shakuntala or the other technology demonstrator, were all tech demos. They went and proved hyperspectral was possible, but we now needed to make it better. We needed to get the resolution to 5 meters. We needed to make sure the lifetime of the satellites are 5 years or more. And we needed to make sure that they beam down a significant amount of data. So this is what you're looking at. After about more than 2 years of work on this R&D design, we finally have these satellites now ready to ship out and launch early next year with SpaceX. So on the top you see is our flagship 5-meter hyperspectral camera covered with a MLI blanket to make sure that the thermal performance is not affected by the varying temperatures in space, and everything below that is your satellite bus that is also completely internally designed and built. On the outskirts are the solar panels on these sides, and inside you would have the entire avionics package that houses the software that is also internally built and code written internally as well. At the bottom you will find the propulsion tanks and the thrusters protruding out that make sure that we can do station keeping, collision avoidance and everything else, and yeah, the rest of the things like the reaction wheels, magnet torquers to orient the satellites are all present inside that. So that's what you're looking at.
Right. So I think we should go into details from the top down.
Sure.
Let's talk about the camera.
Yeah. So this is what we call the Agama camera, which is our 5-meter hyperspectral camera, right? So the issue with hyperspectral cameras have been, when you see what NASA has done or ISRO has done, they've generally been at 30 meters, because if you're capturing more than 100 wavelengths of light, which is what hyperspectral cameras do, then you are compromising on the spatial resolution. Now our customers really want the hundreds of wavelengths, but they also don't want to compromise the spatial resolution. So we have been able to, for the first time in the world, get it down to a 5 meter spatial resolution native from a 550 kilometers altitude. So if I take 550 from the surface of the earth as the baseline, I'll be able to get a 5 meter resolution. If you bring it down, the resolution gets better. If you send it up, it gets worse. So you have on the back side the electronics that make sure that the photons converting into electrons are, taken through an ADC converter, and you have stored the digital format. In between, you have the sensors, the detectors themselves that take in the photons and split them into different varying lights. And the majority of the front part is your mirrors and lenses that take in the light and make sure that the quality of photons that is hitting the detectors, the hyperspectral detectors, are of a high quality. So that's this camera. So this is covered by a lens cap, obviously, because you don't want dust specks to be sitting on the lens. It will be removed before flight, as you can see, just before it is integrated with the launch vehicle. As I mentioned, on the top is the multi-layer insulation blanket, which is covering a majority of the satellite across all the parts, which is what gives it the golden sheen. This makes sure that when the satellite is moving from the sunlit portion of the orbit to the eclipse portion of the orbit, the temperatures vary significantly. They can go as high as 50 degrees Celsius, and it can go as low as -20, -30. And the longer you are there, because you usually have about 60 minutes of sunlight, 30 minutes of eclipse, and they keep sort of changing around in a sun synchronous orbit that we send. This makes sure that variation isn't felt as much towards the internal parts of the satellite. This one is a passively managed system thermally. We don't have active coolers here because we don't need them. In the future versions of the satellites, the honeybees, we will have an active cryo cooler on the sensor as well to make sure the performance is even better. That's the only place we'll have something active. This one is completely passive. You usually provide ways where through convection and through radiation, the heat is basically transferred out for the things that are being generated. So for example, we can't operate the camera for the entire 60 duration stint because the sensors tend to get really heated and you need to pause for a while so that heat is drawn away from the sensors and they can restart it again. So the MLI blanket sort of helps with that.
Okay, just as a small pointer, while Awais you see here is pointing to the satellite and explaining what's inside it, we will go into this deeper, as I said, later when we go into the other room and there is a opened satellite 3D model there where we can see properly what's inside. So for now, listen to him and later we'll go deeper.
Probably the first third of it, you will find the avionics packages. So one avionics package is obviously taking the data from the camera, but that's not enough. You need to take it and then you need to parse it in a way that can be corrected here on ground. That this sensor, there are 4 detectors inside, that the data being captured by those 4 is properly oriented. You are matching it with the rest of the parameters like the GPS coordinates. Where was the image? Where did it start? Where did it end? What orientation did the satellite think that it was in? What axes and what specific attitude the satellite was looking at? And the rest of the things to make sure that we have an onboard computer that is basically running the satellite, telling it what to do in different situations. And we have a board that also looks after the power systems as well, making sure that the algorithms to orient the satellite towards the sun pointing mode, to make sure that the monitoring the battery and other parameters. So there are sensors all across the satellite, from thermal sensors to various different kinds of sensors that are telling you what is happening at the satellite. All of that is being monitored. If any of those goes beyond the normal range that we have specified, the onboard computer, the OBC can decide whether it wants to take the satellite to a safe mode or continue to do that, right? So that all has to happen automatically sort of up there. The second, third of the satellite predominantly has your reaction wheels. Reaction wheels store and release momentum, and by rotating the reaction wheels, you can orient the satellite in an orbit to see where you want. You also have magnet torquers that also do the same thing, but they use the interaction with the magnetic field of the Earth to be able to do that. And then you also have the bottom third is predominantly your propulsion systems. Here you will see where we use the fueling ports and the oxidizer ports for putting in the fuel and the oxidizer, and there are thrusters that would be protruding from the bottom. The bottom third predominantly has tanks that store the fuel and the oxidizer that you can control to basically use it on the thrusters. We use thrusters predominantly for one, at the beginning of the mission, if the satellite is not specifically at the altitude we want, the thrusters can help us increase or decrease the altitude. One. Second, predominantly, a significant chunk of the budget is for station keeping. We want to make sure the satellite lasts for 5 to 7 years, which means that it needs to be maintained at the same altitude for that duration of time. And the third is you predominantly use it for any collision avoidance in case there is a risk of a collision with some other satellite that you keep getting alerts for, as well as for deorbiting at the end of the life, because you can't leave the satellite just as debris up there. You need to bring it down within 5 years of the completion of the lifetime. So yeah, that's what the satellite predominantly is made of. At the bottom is your separation ring, which is interfaced with the separation system, a ring-based separation system that will be interfaced with the rocket, that basically helps eject the satellite from the rocket to the orbit.
Okay, so coming to that camera, it's fair to call it a telescope.
Yes, it is a telescope, yeah.
Okay, so what kind of configuration? Is it RCT or?
I don't think I can go into the details of.
Okay, this is a non-premature interruption here, but look, their optics is their USP. So obviously they can't talk a lot about what is going on in there, but I would guess it's a telescope, since I mean it looks like a telescope. It's round, must be similar to our Chandrayaan-2 OHRC, which is the optical high resolution camera, which is the highest moon camera around moon. So light comes in, strikes the mirror, reflects into the sensor, going through a bunch of optics, something like that. But yeah, anyways, and that sensor thing I will talk later down the video about what kind of sensor they are using. But the earth reflects a lot of light, and in that case a lot of energy as well. Like, is it hot?
It doesn't get too hot from the albedo or the reflection from the earth as such, right? If we were not operating the camera at all, then there would be no issues generally, because the design of the camera itself, the margins that you have for the change in, let's say, your focal length, or the distances between your lenses, distances between your mirrors, that doesn't change as much through the combination of the material that we use. In some case titanium, in some case aluminum, in some case something else, to make sure that the heat and the cold doesn't really change the performance parameters. So that margin is already built in. The issue predominantly, at least with the cameras, is when the sensors are operated for a long duration, they then start to heat up. So you have to pause, let the heat get directed out, and then restart it again. But the lenses and everything else are designed for between minus 20 to plus 50, minus 20 degrees centigrade to plus 50 degrees centigrade.
So is that like a mechanical shutter to shut it down, or
there is no
just electronic?
Yeah, just electronics. Yeah.
Okay.
So once we remove this lens, there is nothing else that we need to do to make sure that the satellite works. You just point it where you want and start clicking. Generally, some cameras also have a deployable once it's launched, but we have heard risks where sometimes it doesn't deploy, then your entire satellite is a waste because it doesn't open. So this is only until the launch, and then we will remove it just before it gets onto the launch vehicle.
Yeah, before more questions on the camera, I see 1 and 2, 3 satellites here.
Yes.
So how many will be on the first launch, and how much do you want in the orbit? Fireflies.
Yeah, so 6 are being built as we speak here. So 1, 2, 3, 4, 2 on the other side at the back there. Out of these 6, the first 3 will be shipped out in less than 10 days from today. And they're launching in January with the SpaceX transporter mission that will go up. 3 more will be followed in a couple of months after that. So 6 will go up early next year before, in just the first few months of 2025. The plan is to have about 12 to 18 of the Fireflies in total. There's our Honeybee satellite also that's launching next year, which will extend the wavelength range of what we can see. And we will launch at least 6 of those, maybe 12. So 18 Fireflies and 12 Honeybees, but the number is dependent on the demand that we see. So on the minimum side, let me summarize, at least 12 Fireflies and 8 Honeybees, but there could probably be 6 more of each.
So just always for scale here, it is roughly 0.7.
Yeah, I would probably say it's 0.7, 0.8 meters in the height here. These you would generally probably be 0.4 cross 0.4 or a little bit lesser than 0.4 meters cross 0.4 meters.
And Honeybees will be?
About 1 meter cross 1 meter cross 1 meter cube, roughly, yeah.
Next up, I'm going to ask Awais a lot about filters and bands, and I know most of you wouldn't understand it. So here I really recommend watching my hyperspectral video, but regardless, if you haven't, let me give you a smaller explanation. See, basically there's a world beyond your red, green, blue that you see with your eyes, right? One example I like to give is take your phone, turn on the camera and point it towards your remote, which has a IR LED on top, and just press any button and you can see it glow. But you cannot see the same thing with your eyes. That is because this LED is glowing in infrared, which is like just beyond your vision, right? And one fun fact is vegetation, your outside trees and all of that, it is not green, it is IR, it is infrared. It's just if your eyes could see infrared, vegetation will be glowing in infrared. One way to take advantage of this from the satellite is put a sensor, put a camera that can record in infrared. Look at the stadium. The center looks like grass, right? It's green, must be grass. But if I look at this in IR, you can see that it's barely reflecting. That is because this is AstroTurf. It is fake grass. More such examples are there in my hyperspectral video if this has interested you, right? You can also use this technique to detect how healthy a plant is. So if a plant is reflecting a lot of IR, it's healthy. But if it's not, it's probably dying. In fact, the drone manufacturer DJI has released a multispectral payload. One of the few cameras on that payload is a IR camera. And then they have this whole software suite from which you can tell if your plant is healthy or not based on reflection of IR. Pixxel and their camera can see IR, but not only can it see IR, it can see like almost 100 flavors in that IR, 100 different parts of IR range. What this gives you capabilities, not just look and say, oh, there is vegetation here. It can look at the vegetation and has the ability to tell what kind of vegetation it is. Is it rice? Is it some neem tree? Is it some apple tree? This is a unparalleled capability that hyperspectral gives you, where like most multispectral or other satellites, you're not just looking and saying it's a tree, it's a crop. You can tell the exact species of the tree or the crop. Now, how many divisions can it see? This is what I mean by bands, of how many frequencies of light can it see. But why did I say filters? See, if you see ISRO's hyperspectral satellite or some other hyperspectral satellites, you'll see they're huge. That is because these have a huge prism like thing inside and many optics, which when the light comes inside, they split it with different kind of prisms and optics and makes it bigger. But what Pixxel is doing is they have filters of different frequencies in front of the sensor, so they can gather IR, they can gather red, they can gather blue and others. It's not as simple as I make it sound though. It's much more complicated.
Okay, so more questions on the camera. How many wavelengths can this do?
So this camera can capture 150 wavelengths of light.
150 wavelengths?
150 wavelengths, yes.
And I think in my previous video when we had met, you had spoken about your filters on the sensor.
Yes.
So it's still
it's basically the same function. The filters that we use, we vary the thickness of the filters and we select the material of the filter so that certain wavelengths of photons are let in at that particular line of the sensor. And as you move down the line of sensors, there are different wavelengths of light being let through. So it starts at 400 nanometers and it goes all the way to 900 nanometers, visible and near infrared. The honeybees will start at 400 nanometers and go all the way to 2500 nanometers, short wave infrared. So how do you make sure that the exact wavelength of light is being captured? You use these filters, the thickness of the filters and the material of the filters. So across the entire range here, there are probably 3 or 4 different filter masks that make sure that only those wavelengths are being let through at that row line, and then you integrate it all, and basically when you capture different images of these, it stacks up and then you have a hyperspectral cube of different wavelengths.
Right, yeah, I've explained that in a video. You all can go watch that video. One thing was, how do you calibrate these filters, like 150 filters? How do you know they actually...
Yeah, so there are light sources that come at very specific wavelengths. So we capture light from the sensors first, and then even it's a camera as well at different wavelengths across the entire range we just talked about. And you start at the beginning and you keep on, traversing through the wavelength lights through different light sources, and you see the response, and then you see what the response is at each of those wavelengths, and then you sort of map it. So one, you've calibrated it, and second, you're making sure that it also captures it at exactly those places.
So basically on ground you put something in front of this camera which will shine different kinds of light.
Yeah. So there are varying levels. At the most basic level, you start with halogen light sources, for example, or other sources that have very specific wavelengths that this is going to be the spectral response of that light source, and then you see how the response is and whether you're capturing that entire thing. And if you use multiple light sources that cover that entire range, you know, that's like the most basic level. We also have a very specific, radiometer cube that has light sources at very specific wavelengths and specific intensities, which you basically put this lens here and you shine the light sources and then you see the response.
Yeah, so
here I mention Aditya L1 SOOT instrument. So Aditya L1 is India's solar mission at the L1 orbit. It has an instrument called SOOT, which is the world's most advanced UV telescope. I made a 3D video on it. Basically, it has a mechanical shutter inside. Also, it has a rotating disc with different kinds of filters. So it will capture the sun in different wavelength. One issue that often scientists spoke about while talking to them regarding SOOT was that the filters degrade over time, right? So today you have 100% performance, tomorrow it might decrease and it will keep on degrading because you have so much energy and light going through it. So that is what I will ask Awais about if they have the same issue.
Not similar, but Aditya L1 had this camera called SOOT.
Yes.
And they had a mechanical filter rotating.
Correct.
One concern they were talking about is that the filter eventually will degrade. With life, they were able to model it. That would you also have the same problem where the filter?
Yeah, I think most things in space degrade. The question then becomes how many years after it degrades. The lifetime generally of the cameras we are looking at is up to 7 years, and the satellite lifetime is also 5 to 7 years. So for those years, it shouldn't degrade to a point where we can't use it. The responses will change, which is why before you launch it, you need to capture a calibrated light source, which is what we do, and see what the base response is. And then what we do at varying intervals is the satellite points towards ground sites where they're maintaining certain ground truth for radiometric accuracy. You can also point it to the moon because the moon has a very uniform radiometric response at all points in time. So all of that makes sure that you will see that it has degraded by this much or the response has come down by this much between the last time and this time. And then you can correct for that when you're looking at the images. But they don't degrade to a point where your image quality becomes so bad that you will start seeing issues in usage of that quality. And just to add that the scientific level of expertise you would need for something like an Aditya L1 sensor is a little bit different from here where you're looking at the Earth. You're still able to see a lot of things, whereas I would guess that it would be a lot more stringent requirement for
and also they don't have a ground truth as such.
So now I will explain, I will remind him of how SOOT does calibration. So what SOOT has this, along the plane of the light, through where light passes, they have this ring of all the frequency LEDs that their instrument is calibrated to. So every few days or few months, they can shine the LED and hence they can measure if their filter is degraded. If their filter is degraded, they can then calibrate and account for the degradation in their scientific data. So this is what I ask Awais and see if they do anything like that.
Yeah.
So what they did was they had LEDs in line with that image plane.
Correct.
So they could I think it had 12 or 18 filters.
Correct.
So 18 LEDs of different wavelengths to calibrate it periodically.
Yeah,
so you have onboard.
We don't, right? So there's two ways to do that. One, you can either put an in-orbit calibration source, which is generally put in the satellite itself, but that adds a lot of cost and complexity. But in their case, they don't have an option. In our case, we have the option that there are these RadCal net sites that are open source that we can just capture and see and compare what the difference is. We can also look at the moon and we can look at the Pacific Ocean in the dark, and that also has a very specific spectral response, radiometric response. So all of that means that we don't need an in-orbit source for us to calibrate. We can look at other sources and see how that's changed and then accordingly correct for it.
Right.
So in the next part, I will mention something called spectral signature. See, everything has a signature, right? But if I talk about light signatures, if I talk about your light signature, if I talk about Awais's light signature here, suppose, his graph would reflect highest in blue, probably. There might be some reds and some greens here and there. So this will be Awais's spectral signature regarding light. Similarly, rice can have different spectral signature versus a apple tree. But like I said, Pixxel has the capability to drill down on the species. So within the rice, Basmati rice and normal rice could itself have different spectral signature. Maybe they reflect a certain part of IR more, certain part of IR less. How you measure this spectral signature is, you will have to go to the field with a spectroscope and measure this. Now there are some agencies that have pre-measured this, but I wanted to ask Awais if they are doing any of this themselves. And also you have to do atmospheric correction, because remember, you're looking from space through the atmosphere. So the red on ground is different from the red that you're seeing through space, because there is air in between, right? There's atmosphere in. So I was asking him about that.
So with this 150, you can differentiate between like two different kinds of fruits.
Exactly.
Trees,
Yeah, we can forget about like two different kinds of fruits or different crops. Those are kind of easy. But even between, let's say, this type of rice versus this type of rice, Sona Masuri or Basmati, you'll be able to say that this is Sona Masuri and this is Basmati, because the spectral signature might be similar, but it's slightly different because they are different types of rice as well. So subspecies detection is also something that can be done with the 150 wavelengths. Yeah.
So do you go on ground and like take a spectroscope and find spectral signatures of say sonar basmati or
for those things we don't ourselves do it. For there are some things that we do it ourselves. Like for example, let's say mineral exploration, or let's say oil and gas refineries and hydrocarbon seepages. There are things that we do work on it, but thankfully, you know, for example, the Indian Center for Agricultural Research, they have spectral responses for a lot of these crops already done on their own, and we can just use that data set to do that. The United States Geological Survey, USGS, has a significant amount of spectral signatures that they also sort of store as a spectral library. So we don't need to do all of it ourselves, thankfully. So we can just use existing libraries, but there are some that we also capture through drones, through handheld spectrometers.
Okay, one thing during that hyperspectral video I noticed was atmospheric correction. Does the atmospheric correction, the way you do it changes because you have such a high
It does.
GST?
It's a lot more, it's a lot tougher to do atmospheric correction for a hyperspectral camera than it is for a multispectral camera, just because the number of bands you have to atmospherically correct for each of those bands, and that it differs slightly. That almost all happens on the ground, right? So we capture 150 wavelengths of light. Thankfully, some of those wavelengths of light also have captured data for the atmospheric number. So in fact, we use data captured from some of the bands that are taking atmospheric responses and use it in our correction model to correct it for the rest of the bands, alongside other open source data sets. So we have ModTran. There's a atmospheric correction model called ModTran that is sort of open source out there. We have built a lot of things on top of that, which is internal to Pixxel, that corrects for that using our own captured, but also from other atmospheric sensor data that they collect from some other sources.
Yeah, I think OceanSat does that, where some bands are reserved only for atmospheric correction and then they use...
Yeah.
Okay. I think the internals will be better done in that that model.
Yes.
But anything else you want to show here?
Yeah, no, I think maybe we can take a look at the satellite without the camera to give you a sense of how that might be. Yeah, so the camera is not integrated on this satellite, for example. So you'll see that here is where the camera goes. So as I was talking about, the optomechanical structure is designed in such a way that you make sure that the heat is being derived from the detectors to a certain point on the optomechanical structure itself, and then through the bus here. So here is where the camera is put. These are antennas that you will use to communicate down with the Earth, S-band antennas specifically for telemetry and telecommanding. And yeah, the rest of the thing is broadly here. Sadly, we are at a stage where we'll be shipping them out soon, so you won't be able to see how it is. There's a star tracker that is protruding out from here as well, which is used for calibrating and knowing where the satellite is. You look at the star field, and when you look at the star field, you can basically tell which point in the orbit you are and where you are orienting very specifically, very precisely with a star tracker. You use GPS also, you use sun sensors that are at different parts here to tell you that the sun is at this orientation, the stars are at this orientation, and the satellite knows very precisely which axis and which specific direction the camera is looking at. So we can orient it back and forth depending on whether we are doing imaging or whether we are doing downlinking and so on. The X-band antenna you will see sort of on the other side, which is much more powerful radio for downlinking the data itself.
Gimbal?
It's not gimbal, no. There are no moving parts on the satellite. We move the entire satellite if you need to do something. So when the satellite is imaging, the entire satellite along with the camera is pointing down towards the Earth or at an angle. When you are finished with the imaging and you are coming over the ground station, then the satellite slightly changes its attitude to make sure that the antenna is beaming towards the ground station specifically.
Even there are no focus elements inside the camera that don't move?
There are no moving parts in the camera as well. So you basically design it for infinity. which is basically saying very far away. So when you're 500 kilometers, if you've designed your camera for infinity, you basically are able to sort of capture and see whatever you want. No moving parts, no whirring, expansion and contraction of things on any parts of the satellite. Yeah.
Okay, before we go into the other room to see the internals, how does the moon look like when you point? Like simulated wise, is it big or small? Like
it kind of looks how it looks from Earth, just a little bit bigger, I would say. But
okay.
you are not looking at the moon for looking at the moon. You are looking at the moon to basically get the radiometric response, and it has been like very uniform. Like it's very uniform. It doesn't change between years or months. So whether you're seeing it this month or whether you're seeing it the next month, it should be the same. And so therefore, if you're seeing a slight change in your response from the camera detectors, it means that the filters have degraded a little bit or something has changed there. So therefore, you can accordingly correct for it.
Okay, and like hyperspectral wise,
we are not using moon for looking. We are too far away from the moon to actually identify spectrally what is there.
Right.
If, for example, we were fairly close to the moon, we would be able to identify, okay, here is an ice glacier, or here is this kind of rock type, or here is this kind of mineral. That is something we could do, but for that you need to be a lot closer. The resolution would probably be very poor in kilometers if you're looking at from 500 kilometer altitude from here towards the moon. It's like, it's very far away.
Yeah.
Yeah, but at some point in the future, we do plan on sending these satellites to the moon and capturing the moon, but that will be from lunar orbit, not from Earth orbit. These are, by the way, the interfaces where we make sure that when we're testing the satellites on the ground, we use a simulator on the computer to basically tell. We bifurcate the satellite into basically two parts, if I were to put it very crudely. One part is being told that here is where you are in the orbit. The sun sensors are being given inputs, the onboard computer is being given input, sun sensor is telling you that you're in this, you're seeing this. Star tracker is being told that you are seeing this based on the orbital simulator, and then the other half of the satellite is responding to it. You will basically have the reaction wheels turning to orient itself towards a certain point. You will have the onboard computer and algorithms running to make sure it's moving that way. So we make sure that in the loop the satellite is doing everything automatically through the simulators, and this is the setup to send commands, receive data, and test the satellite. Yeah.
So this is what you meant when you said hardware in the loop.
Yeah, this is one kind of hardware in the loop. This is more of an onboard in the loop simulation, oils. In some tests we bring in the reaction wheels and other things, so it becomes hardware in the loop, but otherwise it's just onboard computer in the loop simulation where everything is simulated. We also take satellites in different parts to, let's say, a 3-axis motion table, which is more of a hardware in the loop simulation testing. You have a sun simulator that is giving you sun, you have other inputs, and then you have a 3-axis motion table that moves around in the way that the satellite would be. So that's like proper hardware in the loop simulation. But if you're only using the onboard system, it's oils onboard in the loop system testing.
This looks good.
Yes. You can take a shot of the 4 if you want. Yeah, so you have 2 more S-band antennas here, the star tracker that we sort of talked about, and here are the valves for inserting the oxidizer and the fuel into your propulsion system. This is one of the sun sensors that will be able to tell the satellite where the sun is.
Oh, the sun sensor is quite small.
Yes. we have 1 or 2 on at least every face to make sure that regardless of which side it is, we can always know which side the sun is, and then it can orient itself back from there.
The star tracker doesn't have those like cone which typically like that.
We don't need it. You basically, if you want a wider field of view, you can basically have a protruding baffle, so as to say, but we don't need it. Right now we will need to remove this, obviously, to be able to, this is removed before flight, but it depends on what performance level that we generally want. With the kind of configuration that we have here, we don't need the additional baffle for the star tracker.
Okay, so these are S-band antennas. So
Yes.
these are only for TTC.
TDC.
So this face is where? Like this face is facing Earth. This is Nadir, this side.
No, Nadir. So if the camera is here and let's say the lens is that side, that will be Nadir pointing.
Okay, so TTC is aiming.
Doesn't matter.
Omnidirectional.
Yeah, it's omnidirectional.
So that side also
especially
there.
for launch and early phase operations, you need to make sure that even if the satellite is tumbling, you are able to at least send TT and C.
Okay, and this is the X-band antenna.
Yes. So you will see that is generally in the same direction as the Nadir pointing, because you don't want to be changing too much between your imaging and your data downlink.
Okay,
And we will have S-band antennas also in the same direction as well, but these are in case the satellite is tumbling and you
okay,
need
so
to
there
make
are
sure.
behind S-band there.
Yeah, no, there will be two more on the other side
two?
as well. Yeah, yeah, you have two more there.
Okay.
And you have here as well.
So 3 sides,
Yeah,
not that side.
not that side. No, I don't think we would need that many.
Okay. This side is plain.
Yes.
So how many solar panels are there? 1, 2 and
3. So you have one here, one on that face, one that hasn't been put here, which is more longer, like in that one.
So this is not there.
The solar panels will open this way. Yeah, this is not there.
Okay, so that side will be the.
Yeah, we try to make sure that even if the satellite is imaging, there's at least some sun angle to the solar panels, so generating some power, if not 100% of the power. And if we had SADAs, solar array drive assemblies, then you could basically orient the solar panels to make sure you're getting 100%, but we don't have that because we don't need it.
Okay.
In the future versions, we will have some SADAs.
Different bell this time around because this is the last time I will interrupt the convo. This is my favorite part of the conversation where we see inside the satellite, and I won't be interrupting. It's a very nice conversation. I noticed the video is a bit choppy. I have to upgrade my camera sometime this year, but yeah, enjoy.
Okay, Awais, I think we are in this room where we have a cross-sectional, fully opened Firefly. You'll be naming each Firefly or?
Firefly 1, 2, 3, 4.
Firefly 1, 2, okay, just keep it simple.
Keep it simple, yes. They're all Fireflies.
Right, so I mean, we have seen this in detail. So all of this will be eventually metal.
Yeah, this
mounts.
is all basically metal. Parts of this are not metal, like, we use carbon fiber and stuff like that, but most of the optomechanical structure is metal here. So the camera that you saw is basically like this before it is covered with the MLI shroud. As I was talking about, the first third is predominantly your avionics and onboard computer box. It basically is your brain of the satellite, keeping a track of what's happening, what's going wrong, what is going right, and how to sort of move it along. This is the battery pack, which is for storing the power that the solar panel generate and to provide the power to the satellite when it is in the eclipse period or when enough power is not being generated for something. And yeah, this is basically either your batteries or your avionics. Here you will see the reaction wheels. There are 4 reaction wheels in a redundant form fashion. Even if one of them fail, the other 3 can take up the load of the other reaction wheel that should have been there. You would have magnetorquers there. You would have a magnetometer. You would have IMU. You would have GPS. So the IMU system. There are sensors and there are actuators. So the sensors are helping you with attitude determination. So it's called the attitude determination and the control system. Determination is, it's not altitude, it's attitude. Attitude is the orientation of the satellite, and you need to know exactly which attitude or orientation you're looking in. So the sun sensors that we had talked about there tell you that, okay, if the sun is in this direction, this sun sensor is getting input. If, the sun is somewhere here, then these 2 are getting input. So that way you know roughly at least what direction. They are the coarsest way of start with a baseline of your orientation. Then you use your IMU to know where it was previously. Then you use your magnetometer, which tells you what the magnetic field is, and depending on the magnetic field model of the Earth that you would have, you will be able to tell where you are. And then finally, the most accurate one is the star tracker that we sort of looked at, which tells you depending on the star field and how it's changing, where exactly you are looking at in that axis. So that will tell you exactly that when the camera is looking at somewhere, this is where it's looking at. Let's say it was looking here and then the Earth is somewhere else. Then your actuators come into the picture, reaction wheels, magnetorquers, that tell you that, okay, this is the axis. I need to move from there to here. And as a 3-axis controlled satellite, it basically moves there. So that's what predominantly the middle deck does here. So and bottom deck, middle deck, the top deck. And the bottom deck, as you can see here, is your propulsion tanks. And underneath it, you will have the thrusters that basically do the, you don't see it here, but the thrusters are what will make sure that the station keeps and everything else. So we were talking about antennas. You will see 2 S-band antennas on this side. You will see 2 S-band antennas on this side. There will be 2 more S-band antennas here to make sure that regardless of if the satellite is tumbling or not, The TT&C is always available. You don't want to lose your satellites. You need to be able to command it at all points in time. You need to be able to bring down the telemetry regardless of where it is. The X-band antenna that you were able to see again at the top there, that will need to be specifically oriented because it's a very high data rate system that needs to be downlinking a lot of data. And you have a GPS antenna to tell you about the GPS. You have main antenna, redundant antenna, and so on and so forth. So yeah, I think that's kind of how the thing goes. You have HDRMs at each phase where you have the solar panel. So it's basically a hold down release mechanism. It's holding the panel in, and as the signal is sent that release the solar panels, it basically pushes the panel a little bit so that they can deploy when it is safe to do so after the deployment of the satellite. So yeah, I think all those make sure that the satellite does what it needs to do.
So the IMU has to be in plane with the
correct. So you need to make sure that we basically need to align things properly. So you are looking at what direction the IMU is in, and then you need to use various different ways to see how it is aligned, how well it is aligned with the camera axis. So you need to know before you send it up there how the alignment of your axis is with the IMU here and with the camera, and account for the differences that might still come in measurements, and those can be taken care of once it is in space as well. So yeah.
So the center of gravity will come roughly here somewhere as well, but it will change with the fuel being used.
Yeah, that will be accounted for in the software that we use, right? As the X amount of fuel starts getting used, we have a way of sort of keeping track of that. Then you can account for the CG basically coming down, but most of it is here. So I think roughly you would sort of end up with it somewhere here itself, and then this won't change it as much, but of course it gradually keeps changing a little bit, but the software accounts for that as the consumption increases.
Okay, and so there will be single thruster or
there are four basically.
So I assume from this
yeah, so you have thruster 3, thruster 2, thruster 1 and thruster 2. So you have 4 thrusters that basically make sure that we station keep the satellite.
Angle, like you'll have cosine losses there with the angle, or like pointed straight
They are
down?
pointed straight down.
So you can't use them for, can you use them for like
we can
attitude?
If we need to, we can, but we won't. They are backup in case we need to use them, but we generally won't be using them for any of the attitude control.
Okay. These tanks look big. And also,
those are real. They are to scale.
So what kind of propulsion? I mean, I say 2 tanks. So what kind of, like, is this biprop?
It's biprop. It's green propellants predominantly. We use the thruster system from Dawn Aerospace, so we don't do it internally.
Okay.
Yeah, it's biprop. I can't seem to recall exactly which 2 we use there, but it's 2 green propellants, biprop chemical system.
Right, and the battery?
It's I think nitrous and propene.
Okay.
Yeah.
The battery looks huge.
You need a lot of power in the
significant.
You need a lot of power in the eclipse period as well, right? You need to be able to sometimes start imaging as it is just coming out of the eclipse. So you need to start downlinking, and the X-band radio, the camera end up taking a lot of the power. And if you have not generated the power in the entire eclipse period of the orbit, then you still need to make sure that it's there. Also, you need to make sure that the depth of discharge generally is not going below 80%. So we tend to keep the capacity at 80 to 100 to make sure that the lifetime keeps on going. You can bring it down once in a while below that, but if you bring it down quite significantly, the lifetime decreases drastically. So the reason why it is designed for this much is so you never go below 80% capacity storage here, and for backup in case we are not sun pointing or generating power, then it can last itself for like a few days until we figure out what's happening.
In KSP, the comms take up a lot of power, like they'll drain your power significantly. Is it true in like real life as well, like X-band antenna?
It's one of the more powerful things on the thing, yes. Especially because you need to keep operating it for a continuous duration of 8 to 10 minutes as it goes over the ground station. So I would probably say it's top 3, if not the top 1 in terms of power consumption. Camera being the other significantly power consuming one area.
Right. So what kind of data, like No, first of all, how much time it goes in the eclipse? Roughly half or what?
Not roughly half. So 90 minutes is each orbit, and usually between 50 to 60 minutes you would have sunlit, and then you would have. It's not a purely circular orbit, right? It's almost circular, and the remaining 30 to 40 minutes are in eclipse.
Okay, so 30%.
Yeah.
So how much data are you looking at, like over a cycle, over the orbit?
So it starts at 500 megabits per second, and it can go up to 800 megabits per second with the radios that we have on the satellite right now. And we downlink it at the end of every orbit. So the way that we operate the satellites is we take a long strip of image in one orbit. At the end of that orbit, we downlink all of that as it moves towards the ground station in the North Pole. So we have an antenna near Svalbard, near the North Pole, where we downlink it, and then all of that data that we have captured in that orbit is downlinked, and we repeat a new capture and downlink in the next orbit, and so on and so forth. And so yeah, it ranges between 500 to 800 megabits per second, depending on the quality of the signal, the ground station capture, and everything else.
Because I think that is not appreciated enough, or doesn't come out as enough. This data pipeline that you have to build.
Correct. Yeah, the difference between the demo satellites and this one is the demo satellite could at best do for us about 2 megabits per second or so of data downlink in the first one, and then generally satellites of these size do 50 megabits per second or so. So we are like 10 times better than that, and that creates a big difference because you need to downlink as much data as possible. Capturing we can do always, but if it's not useful if you can't downlink it at the same time in the same orbit that you are capturing it. So the 6 satellites together every day, the first 6 Fireflies that we're building, they will beam down about 1.2 million square kilometers of data a day, which is a significant amount. So we can paint entire India, we can paint entire Brazil, we can paint entire continents in a few weeks, rather than having to do that over many years or so, right? So that's what downlink capacity helps with. So you're right in the sense that usually it's a very overlooked part of making sure that and hyperspectral captures significantly more data than normal cameras as well. So you need to downlink all of that beyond just multispectral or optical.
So that's few terabytes per day?
It's a few terabytes per day, per satellite, yeah.
Okay. So I'll just come from this phase.
Yeah, because we have 16 orbits in a day, and then we downlink almost in 14 out of those 16 orbits a day.
Damn. So per year it will be like few petabytes
of data, yes.
And all of it has to be made available in your tool as well on demand.
Correct. So they come to the ground station, and it through a backhaul goes to Amazon, Microsoft, cloud centers. We choose the geographies depending on who we are serving in India, in US, in Europe. And from there it is integrated with the Aurora platform to make it available. And it needs to be cataloged, stored, so that when you're searching it, you can find it immediately, and all of it has to then be corrected. Once the data comes, it's basically just raw data, level 0. It's not corrected. It is basically very, it has parts of noises in it. And then you geometrically correct it to make sure that it aligns with the map of how you see the Earth. You radiometrically correct it to remove all the other artifacts from there, and then you do the atmospheric correction we talked about as well. Once all that is done, and it needs to be done automatically for all of that data, then you see what we call level 2 data, which is your bottom of atmosphere reflectance product. That is what is used for analysis. That is what you call analytics ready data.
Wow. I'm thinking from like architecture and engineering, software engineering perspective. Just a lot to do. We'll come from these. Can you tell now how the panels will open? They will be this way, one of them.
Yeah, so this is where the camera bore sight axis is.
Yes.
The panels will be kept like this here with the hinges on these sides, and you would have a panel here as well. This one won't deploy. This is right here. On both these sides, you can see the hold on and release mechanism that basically makes sure that the panels are deployed. So this is your solar panel pointing axis. So your basically sun pointing will be towards this side as the camera is imaging down. The sun generally is in this direction in the sunlit portion of the eclipse. So the angle of the sun obviously changes. When we are not imaging, we orient it 100% like exactly towards the sun, so that the power generation is almost 100%. But then as it goes towards imaging, and you need to then make sure that this axis is not changing with respect to the earth, this changes a little bit in terms of the angle with the sun. So usually it goes down all the way to 40% power generation or so by the time it reaches the poles, and then it goes to eclipse. So this is the direction where the solar cells are.
Okay. So these are okay. So this will be the TT. The X band will be somewhere here, I would assume.
Yes, it should be. As we saw in the satellite there, it will be on the top deck, attached at the top right there outside.
Yes, and so one GPS antenna is enough in this case.
Two. We have one main antenna and one redundant antenna. Again, with a predominant.
Even the
GPS.
S-band antennas are redundant, or
there is no redundant. There's so many of them that some of them work as main, some of them as redundant. There's no difference between the S-band antennas. X-band, there is a main and redundant, because we have a main and redundant radio as well. In case one goes down, the other can still continue to do the work. And the GPS as well, one main and one redundant GPS. We generally try to make sure there's no single points of failure. The only single point of failure here probably is the camera. In case the camera goes out, then we're done with the mission. But from a satellite standpoint, in case any one single component fails, the rest of the satellite will still be able to do, in most cases without any loss of performance, in some cases with slight loss of performance.
Okay, and I think the last question. This would face roughly opposite of the star sensor will be roughly opposite of Nadir. What's called anti-Nadir? What is opposite?
Yeah, because if you're looking at the Earth, your star tracker needs to be looking at the star field.
Does the moon come in the field of the star sensor?
Not, no.
No. Does anything happen if it comes?
Nothing happens if it comes. Basically, then it won't be functioning as well. If you're not able to see the star field, and if there's moon there, or if there's sun there, or if there's something else there, then that it becomes a non-zero input into the attitude determination algorithm.
So one is enough in this case.
Generally, we would prefer two, but yeah, in our case, one is enough to get to the pointing accuracy numbers that we need.
Okay. And what is the rough mass, weight of this?
60 kilograms is the weight of a Firefly with the fuel. Yeah. 60.
It looks more. Yeah. I think that's it from me. Unless you have anything to...
No, I think, we talked about, here is one solar sensor.
There's one
here. And then there's, on every phase you have a sun sensor as well that tells you where the sun is. But apart from that, nothing else. We covered most other things.
Yeah. Can't wait.
We can't wait either. It's been a long wait. We were supposed to have been launched by now, but... it will finally launch early next year. We're shipping these satellites out in the next 10 days.
Yeah. Thanks, man.
Lovely
for real. I wish a lot of success to Pixxel.
We can't wait either. It's been a long wait. We were supposed
to. This video wouldn't be possible without the numerous members who financially support this channel every month. Thank you to all of those. If you are not a member, please do consider hitting the join button. It starts from 29 rupees. If you think I deserve more, you can add more. Yeah, live long.
We can't wait either.
Special thanks to Jayam Sharma, Rohit Sarna, Utla Chaitanya, Pradeep Mohandas, Vishal Bharat, Krupal Patel, Shaunak Perni, Kumar Akhil, Chandrabadan Singh, Shrikant Kapri, Moon, विशेष वत्सल व्हाट्स न्यू और विद्यासागर रौनकी।